Hello everyone, welcome to our tutorial AI meets database. So good morning, good afternoon, and good evening everyone. So in this tutorial, we will first introduce AI4DB, which wants to utilize AI techniques to automate database. For example, we use deep learning to estimate the cardinality and the cost of a query, so which can improve the accuracy for estimating the cardinality for multiple fields or multiple tables. And we can also use some reinforcement learning techniques to tune the knobs, which can also increase the performance of the database. We can also use some learning-based technique to recommend some index views to enhance the database performance. On the other hand, we also want to introduce database for AI. So we want to utilize database automation techniques to reduce the burden of deploying AI. So you know that when the user want to utilize AI, they want to load data outside the database and then train the data and utilize data. It's rather inconvenient for users to deploy AI models. So our database community wants to embed AI capabilities inside database. So we can extend CQ to support AI operations, and we want to develop database operators and automators and increase the training time and improve the training performance and the inference performance. So this is the outline of our tutorial. I first introduce AI4DB, and then we will introduce database for AI. And finally, we will provide some challenges and open problems for AI4DB and database for AI. So I first introduce some motivations of AI4DB. So we know there are many new scenarios that bring new challenges for traditional database techniques. For example, we have various applications, and we have large-scale data, and we have diversified workloads. So traditional database rely on human to tune the database, to automate the database, which are not true for large-scale data, for example, on cloud database, because it's very human-intensive work to tune billions or millions of database instances on the cloud. So we must use some automatic techniques to help us to automate the database and to make the database more intelligent and more powerful. And AI is also getting more practical due to three main driving factors, including we can handle large-scale training data, and we can have some more AI algorithm, and we have powerful new hardware, for example, GPU and AI chips. More importantly, different from some traditional machine learning and data mining, which aim to improve the accuracy. So they rely on some training data, and this training data should be labeled by humans. But in database, we focus on the improved accuracy and efficiency. So for efficiency, we can easily to get the results by running some workloads. So we have large opportunity to utilize machine learning techniques to automate database performance. So first application is about learned database configuration. You know that every database has large number of knobs. For example, PostgreSQL and MySQL, and some database has hundreds of knobs. And it's very important to tune knobs to achieve high performance. However, it's very labor-intensive tuning for traditional methods, which rely on some database administrator to tune the database. So it's very promising to apply automatic tuning methods. The second is that the traditional tuning is very time consuming. It usually takes weeks or days to tune the base. So we can utilize some learning-based techniques to reduce the tuning latency. And another point I want to mention that the database or the administrator DBA usually can transfer the knowledge because they can utilize some knowledge and transfer knowledge to other database instances. But for the learning-based techniques, this is much harder than human. So when we apply machine learning techniques, we need to consider how to improve the adaptivity for the different database. For example, we want to the learning method to adapt to different workloads, different database instances, and different database systems, and different hardware. So I think this is rather challenging, and the database community are working on this to improve the adaptivity for the machine learning techniques inside database. So the second one is learner-based query optimization. So we can utilize machine learning techniques to address the hard optimization problem. For example, cardinality estimation. Traditional method usually utilize some histogram, a sketch-based method. But for multiple columns and multi-tables, it's rather hard because different columns and different tables have some correlations, and the training methods are hard to capture the correlation. And the second one is join order selection. So for example, given 10 tables and there are billions of possible orders to join the tables. So it's very important to get a better join order. So if we want to explore every possible join order and then select the best one, it will take lots of time. So you know that selecting best order has two parts. The first one is select the order. The second one is utilize order to run the query. Both time are very important. We need to very quickly to identify the order, and the order can be run by the database very fast. So we need to find the best order very efficiently. So the third one is about learner database design. So you know that there are lots of work on learner index. The traditional B tree may have some problem, for example, concurrency and some size and some pointer chasing and catch miss in memory. So can we utilize some learning-based index to replace the traditional B tree index? There are many attempts to address this issue, and there are lots of work. And there are also some other learned data structure. For example, learned transaction scheduling. Can we schedule the transaction to avoid conflict between different transactions so as to improve the performance of running these queries? So I think there are lots of opportunities. And also some learned database diagnosis. I think this is also very important, especially on the cloud. You know that we have billions of database instances, and it's rather important to diagnose the system and slow queries. So can we utilize machine learning techniques to monitor database activities and diagnose the system and find the root cause for each failure? I think this is rather important. We can utilize some learning-based technique to help us to diagnose the database. And next is database security. So database security is also important. For example, how to automatically to discover the sensitive data and detect anomalies of database. For example, whether some user wants to attack database, and whether we can detect the sensitive data, for example, the card number and the ID number. So we want to automatically to do this, not labeled by human. And we also want to avoid the SQL injection and some anomaly access of the database. I think that this can also be relied on the learning-based techniques. And there are some database systems that also want to try to utilize machine learning techniques to enhance database. For example, Oracle wants to tune the knobs to recommend the views, knob tuning, and OpenGhost new database that also utilize AI techniques to optimize the whole life cycle of the database system, and also including some database tuning index and view advisor, and they're also working on some kinetic cost estimation and joint order selection. And auto tune. This is a new company by Anipolo that want to use machine learning techniques to optimize database to tune knobs. So I think there are lots of opportunities that deploy some machine learning technique inside the database, and this call for arms from the database community to work on this and to make database community much stronger. Okay, next I will introduce some techniques for database for AI and AI4DB. I will first introduce AI4DB. I will first introduce some techniques, and then my students and college will introduce some other components. First, I want to introduce knob tuning. So the motivation is that there are lots of database knobs, and it's very important to tune the knobs to achieve high performance. More importantly, the knobs are correlated, and they have some correlations, and it's rather hard to tune the knobs. And the knob tuning also affects the database performance. The traditional database usually rely on DB to tune the database, but for large-scale database instances, the DBA cannot tune many database instances. So we can rely on some machine learning techniques to achieve this. And the next, I will introduce a workflow of knob tuning. First, for example, a user finds that the database is slow, so can we tune the knobs and to make the database faster? The first step is that first the tuner, the automatic knob tuning system will request workloads in recent, for example, hours or weeks, and run the workloads on the database system, and then activate the workloads in the database system. After activate the workloads, we can get some matrix from the database. Based on the matrix, for example, we can find how can we tune the knobs. So there's some correlation. We can learn the correlation between matrix and knobs. And based on the correlation, we can recommend how to tune the knobs. And we set knobs and to rerun some workloads and recheck the metrics, and then we can tune the knobs further. So in this way, we can make the database run faster. So there are some challenges. For example, how to tune hundreds of knobs. And more importantly, the knobs are not independent, and most of knob values are in continuous space. So it's rather huge space for the knob combination. So so for database, can we effectively use large-scale data to tune the knobs? So you know that for the database vendors, it's rather hard to get some large-scale experience data, especially on the production machine. So because they do not want to remember many workloads. So how to get workloads to tune the knobs is also a challenge. So can we do not rely on large-scale training data, especially some data from the production machine or node. So the second, how to adapt the tuning method to different scenarios. For example, different workload, different system, database instance, and different hardware. I think this is rather challenging. So we can broadly categorize the existing tuning methods into 5 classes. The first one is a heuristic methods. In this method, they want to get some training data, for example, the training workloads, some workloads with some best knob tuning knobs, and then give a new workloads, they find some similar workload and recommend some knobs. This rely on the training data. The second one is machine learning pipeline-based method. So they was first one to categorize the workloads and identify the most important knobs, and then use the machine learning technique to tune the knobs. And the third one is untrained reinforcement learning-based method. So this method based on, for example, give a database, they want to run some workload on database and then tune the database based on the workload running and some metrics report from database. And the deep learning, they also rely on some training data that capture the relation between the metrics and knobs. And the last one is there are also some works on tuning some memory-based database, for example, database and Spark, tune the buffer size. So the first method is search-based tuning method. So this is some heuristic-based method. First, they want to get some training samples. They divide some knob range into key intervals and sample some settings for each interval, and then give a new workload. They find some similar workload from this training data, and then based on the knobs for this training data to recommend the knobs. So this is rely on some training data. This is some limitations. So it wastes some time to searching the knobs, and it cannot learn from heuristic tuning, and needs to restart the procedure from scratch each time. And they also need some training data. The second method is about machine learning pipeline. So they first categorize the workloads and identify the most important knobs that may affect the performance, and then tune the knobs based on some machine learning techniques, for example, Gaussian process recognition, so tune the knobs. So this is a pipeline-based methods, and it also needs to use some training data. So this pipeline architecture, so where the ultimate solution may not gotten because it may fall in some local optimum, and it's also rely on some high quality training samples. And if we have such training samples, it's okay. But if we have no such training samples, it's rather important to get there. The next method is end-to-end reinforcement learning for tuning. So this basic idea is that, so we want to utilize some reinforcement learning to tune the knobs. So given a database system, and for example, this is a database system, and we have a tuning agent. So this is our tuning algorithm. So there are some actions. The tuning agent will apply some action. The action means that we want to increase the value of knob or decrease the value of some knobs. So when we apply the action, so we run the workloads on the database, and the database will report some metrics. For example, the transaction commit number, the tuple fetch number, and some conflict number. And based on the metrics, we can capture correlation between knobs and metrics. And we can also get the performance change after we do the action. So in this way, we can capture the correlation between the knobs and the performance, and the knobs between the metrics. In this way, we utilize correlation to do some new knobs. For example, give a new workload. We run the workload and we get a matrix. Based on matrix, we know, okay, how can we tune the knobs? So this is a pipeline. So for example, which knob we want to tune. For example, the cache size, the checkpoint timeout, IO concurrency. So we have six important components in here. Agent means the tuning system, environment, the database instance, and state, some metrics, and action, the tune the knobs, policy is the how to capture the agent. And the reward means that after we tune the knobs, how can we evaluate the tuning? So this is the reward. So if the performance is better, we give a positive, otherwise we give a negative. So here are some important techniques we need to consider. For example, how to select good reinforcement learning methods. So because both the state and action, the state means the matrix and the action means the knob tuning. So both of them are in continuous space. So we need to select algorithm that supports the continuous space. So it's important to select some policy-based method, for example, DDPG. The second issue is about the reward. So when we tune the knobs, how to evaluate whether the tuning is good or not. So the reward is important. So we need to capture both the long-term reward and short-term reward. So it's very important to design a very good reward function. So later there are some methods that want to support a query level. So the methods I mentioned only support some workloads. Given workloads, supports workload tuning, and they tune some parameters, knobs that affect who did this. But some users only want to improve the query level. For example, we want to increase the performance of single query, and for example, a slow query. So how to optimize the query, a specific query or the specific type of query. So we need to capture the query encoding and the input encoding into the tuning. We can also support some session level. So for example, we want to optimize the query in this session. So in this work, the author proposed different tuning granularities to achieve the performance for different scenarios. And there are also experiment paper for the tuning works. For example, they want to compare different methods, for example, Gaussian process, deep learning, and reinforcement learning. And they want to know the pros and cons of different methods. So there's some conclusions from the experiment paper. For the tuning performance, they are better than DN and better than Gauss processing. And Gauss processing can convert quickly, but may fall in some local optimal. And DNN, DL, and require some more training iterations, but find the better settings for adaptability. So DNN, DL, and better than Gaussian process and tuning time. And the tuning time, if we want to run workloads, the running workloads take much portion of the time. So important to reduce the training time. So there are lots of work on tuning the buffer size. For example, the buffer is very important and to meet the user requirement, for example, SLA, service level agreement. So for example, the user wants to execute query within 1 second, how can we tune the buffer? If we can increase the buffer size, the query may be faster because most of data will be in memory. But if the performance already meet the performance from the user, we can decrease the buffer size. How to evaluate whether the buffer size is enough to meet the SLE? I think this also is very important. And there's some learning method to work on this. And the next one is the buffer size tuning for Spark. So you know that Spark have many knobs, and the knobs in different levels, for example, resource management level and container level and application level. And in each level, there are some knobs, and these knobs have different effects for the performance. So how to capture the correlation from different levels. And next, how to select important metrics from each label, and how to combine the metrics and knobs from each level. So they work on this, and they use some direct based optimization to combine the different knobs from different levels. Here is a comparison of different methods. We compare different methods in different rows, and for each column is different metrics. For example, the tuning quality and the tuning latency and workload adaptivity and database adaptivity and hardware adaptivity. So we can say that the usually manual tuning usually have high tuning latency, and some heuristic can adapt to database, but it relies on some training data. And reinforcement learning can adapt to different database and hardware. And deep learning, because it relies on training data, so it's not very easy to adapt to different scenarios. So some takeaways. So learning-based methods can find the better norms than some search-based methods, and learning-based methods can take long training time because they need to run some workload, and it's very important to study the adaptability to different database, different workloads. And there are also some open problems. For example, we want to predict workloads performance after the knob tuning. This is also important. We need to convince the user that after you tune the knobs, we can make the database run faster. How to evaluate this and how to guarantee this. And the next one, how can we use one tuning model to fit different database? So we have different database, PostgreSQL and MySQL. Can we have a single tuning model to support different case? And can we utilize some knowledge information? Because the human has some knowledge and human can inference and read it. But for computer, how can achieve this? Okay, next we will introduce some other components for database optimization.
Hello everyone, I'm Xuanhe Zhou from Xinhua, and my supervisor is Gu Liangli. Next, I introduce View Advisor. View modularization is rather important in DBMS that utilizes views to improve the query performance based on the space-for-time trade-off principle. However, it's hard to automatically generate materialized views for ordinary users. Traditional methods rely on DBAs to generate and maintain materialized views. Unfortunately, even experts cannot handle large-scale databases. So let's first see the workflow of automatic view advisor. Given a set of queries, the view materialization just generates a collection of high-quality views to optimize for the future queries. It includes extracting the common subqueries and then estimating the performance and selecting from the subqueries as materialized views, and finally, rewriting the queries with materialized views. What's more, we also need to consider when and how to update and remove the useless materialized views in the future. We can divide existing MV works into MV selection and MV eviction. MV selection is an NP-hard problem, and there are many problems in heuristics. First, traditional MV estimation is based on empirical equation, but it makes no sense when MVs change the query plan drastically, because it's hard to estimate the future refresh cost. Second, heuristic methods take MV selection as an IRP problem and use greedy or heuristic rules to solve it. However, the performance can be very bad with assumptions like MVs with higher costs can have higher utility. Besides, traditional methods need to estimate the credit, that is the sum of future utility and the recreation costs, to decide whether to build the MVs. So, Oracle has proposed a hybrid MV selection method. The greedily select the MVs and predict trends with machine learning. It first generates candidate MVs that balance between conflict queries, and then it enumerates queries MVs and estimate the query costs with or without MVs. And finally, it selects the MVs with maximum cost reduction to actually implement. Besides, it also provides MV refresh, which predicts MV usage with a neural network. And if the usage has degraded to a threshold, they will drop the MVs. However, the downside of this method is that it still takes quite a long time to enumerate MV combinations and cannot ensure high performance with heuristic pruning. So to address these limitations, Yuan has proposed to use reinforcement learning to address view selection and maintenance problems. First, they use a wide deep model to estimate the benefit of using a materialized view to answer a query. Second, they model the view selection as an integer linear programming problem, or LP problem in short, to use reinforcement learning to find the best policy. However, they assume that the workloads do not change and cannot adapt quickly to different new workloads that have different query patterns. So to address this problem, we has proposed an encoder-decoder-based view advisor, which first extracts common subqueries across all the user queries and uses a deep encoder-reducer model to estimate all the queries together with the candidate MVs, and will take the embedding vector for the ARM architecture to select MVs. So the core idea here is the encoder-reducer model that can encode both the queries and the materialized views, where the encoder is an RN network that just embeds the query features, and then the reducer will encode the encoded query features together with the candidate materialized views into an embedding vector. Next, they utilize an attention mechanism to learn the relations between the query plantries and the view plantries, and will take both the attention vector and the hidden vector of the encoded reducer model as the state vector of the IR architecture. In IR, it takes the attention and the embedding vector as the state, and the agent decides whether to implement which MVs based on the state features, like common subqueries that do not have MVs. However, this method do not consider when and how to drop materialized views. It's challenging to decide whether the created MVs actually take effects for current workloads. So, how to drop the created MVs when there is no enough disk budget? For view eviction, a credit-based model is proposed that evicts materialized views with the lowest credit when the storage limit is reached. Higher credit means that we will sacrifice more utility if we evict the view. However, because they train the R model with the runtime of workloads, it assumes that the database environment will not change. This results in a high cost of model training, especially in the code startup step. In this table, we have summarized the advantages and the disadvantages of different selection methods. And then we can see that the encoder-decoder model has achieved the highest quality because it encodes the query features together with the materialized view features. And based on that, the IR agent can decide which materialized views can achieve the highest utility, while other methods only based on some heuristic rules or the subqueries only. Besides, the MV eviction methods have achieved the highest adaptability because it can dynamically decide which materialized views are actually useful based on the incoming queries. So in conclusion, learned MV utility estimation is more accurate than traditional empirical equations. And the learn and wait utility estimation is more accurate, especially for the problems like multiple and wait optimization. And the learn and wait selection is more robust than heuristic methods. And learn and wait selection works well in online service, but takes much time for model training, especially for code start steps. And the query encoding models need to be trained periodically, especially when the data are updated. And there are some open problems like unmade benefit prediction for the incoming queries. And the cost of unmade initialization and the future updates, especially for the learning-based methods. And besides, we need to decide how to support both unmade updates and unmade evictions together. Next, we are going to introduce the index advisor. In DBMS, indexes are the key to speed up query execution, and one of the most important problems is index selection. First, to build an index for specific query and get a very high cost reduction. However, index selection is an hard problem. It needs to select from numerous candidate indexes. Besides, it's not the case that we build more indexes and we can gain higher performance. If you build some redundant indexes, they may consume too much memory space, increase the maintenance costs, or even cause negative effects. So first, let's also see the workflow of the learn index selection. Given a set of queries, you need to generate a collection of indexes to optimize the execution of queries. So it mainly includes 4 modules, including the circle feature extraction, index benefit estimation, index cost estimation, and the index selection. And we can see there are many challenges in index selection of each module. First, it's hard to estimate a benefit since there are multiple features like execution time and the space budget. Besides, there are interactions between different indexes like a multiple column access where you can build an index or multiple columns. Besides, the set of possible index combinations are huge, and they exponentially increase with the number of columns per index. We have divided in existing index selection methods into offline index selection and online selection. First is offline index selection. The basic method is auto-admin. For each query, it extracts the indexable columns and enumerates for the column combination with the highest index benefit. For all the queries in the workload, it runs top K combinations and greatly adds indexes until arriving the limited disk space. Another similar method models the index selection as a knapsack problem and uses dynamic programming to select the highest benefit index combinations. And another class is online index selection, which is also horizontally. Consider a what-if-based method that divides the workload into epochs of queries. And for each epoch, the profile the candidate indexes for the incoming new query. For the incoming query, it estimates different benefits of the indexes that can be used by the query, and will update the index set based on the newly found indexes. And finally, at the end of each epoch, it will create the indexes with the highest index benefit in the set. However, the what-if-based method, it is laborious to require human beings to design the what-if course. So another idea is we just use the TBAs to estimate whether the selected indexes are good or not, and other things are left for the automatic algorithm. So there is a semi-automatic index selection method. It monitors the DBMS in real time and then dynamically analyzes the workloads and enumerates some candidate schemes. And to tune and enumerate some candidate schemes to tune the index structures. But before implementing the index schemes, it calls the DBAs to judge whether the scheme is good or not. And based on the feedback, the well updates is the selection strategy. At some level, this method has reduced the DBA's burden. And recently, machine learning-based index selection methods just consider whether we can replace the feedback part with machine learning models. So the core idea is that it thinks that it's critical to compare the execution costs of plans and decide the index benefits. In simplicity, we only consider whether we can gain the performance improvement after creating the indexes. If yes, we just build it. If not, we just ignore it. So this method builds an evaluation model to create indexes with performance gains. This table has summarized the differences of both selection methods. And we can conclude that the latter methods mainly outperform traditional methods in index benefits estimation, and the learned index selection can efficiently work in query level, but ignores in the interactions between the queries in the workload. And the traditional index selection, they cannot adaptively balance between the index benefit and the maintenance costs, for which the learning-based methods can do a better job. Besides, there are also some open problems in index selection, like how to build an online learning-based index advisor that can support online index selection and index updates. Besides, how to improve the adaptability for different database schemas and memory capacities. Next, we will introduce the database partition on distributed databases. Most of existing methods are horizontal partition in table level. It's extremely important to place different partitions across the nodes to speed up the query execution and the balanced data distribution. However, database partition is hard. It needs to enumerate many different columns, and the candidate combinations can be very huge. And finally, the existing partition functions like hash or round robin are too simple to process complex transactions, and the range function requires careful manual design. So database partition is to select columns as a partition key for each table and use the partition keys and the partition functions to locate the rows of those tables into different partitions to achieve higher execution performance. So in the following, we'll separately introduce existing works in partition key selection and partition key design. For partition key selection, the first method is search-based, which is mainly composed of 2 steps. For the first step is to maximize the data locality. That builds a table-level graph where the vertices are tables and the edges are joint predicates of each query. And then it derives a maximum spanning tree on the graph, whose edges can be used to co-partition the tables. However, co-partition can cause data redundancy. So in the second step, for each query, it can derive a spanning tree, and to minimum the data redundancy, they recursively merge those trees by dynamic programming. However, this method still brings in much data redundancy in the end. So there is also a deep reinforcement learning-based method. They first encode the tables, query frequencies, and the foreign key constraints into a state vector, and use the deep reinforcement learning model to select a partition key or a replication table at each iteration. They can learn from the reward to optimize the selection policy. It computes the reward based on the costs estimated by the optimizer, which is not available before partition. So in other words, they design a simple cost model based on the neural network. However, this neural network can only work for single queries, and they just ignore the important partition factors like data allocation or concurrent queries. So another problem is how to design the partition functions to support complex scenarios. The first work is for small transactions, which may access multiple nodes and bring extra overhead than on the single node. The method includes three main steps. First, they also build a graph model, right? And the vertices are tuples, and the edges are the transaction relations. For example, for the tuples in the same transaction, they all have edges between each other. And then they use the graph partition algorithm. First, they build a graph model, right? The vertices are tuples, and the edges are the transaction relations. For example, the tuples use the same transaction, all have edges between each other. And then they use a graph partition algorithm like a matrix to locate the nodes into the K partitions. However, until this step, we still do not know how to partition the tables because it uses the range partition function to locate the tuples. Hence, with the tuples as the values and the K partitions as labels, they build a decision tree and derive the partition ranges based on the tree of predicates over values leading to the leaf nodes. However, as declared in this paper, it's not ideal for very large databases or workloads with heavy inserts. Another partition function is for analytical queries that reduce the latency. The also mainly has three steps. First, it identifies the query filters as features, and then we can characterize each tuple with a bit vector, and each bit represents whether the tuple is used in the query filter. And finally, they just found the optimal partition from bottom up with a clustering-based algorithm. In this table, we have summarized the differences of the partition methods. And we can see the learning-based method, like a DRL for the partition selection, they can achieve the highest quality by considering more partition-related features and use the agent, the R-based agent, to explore and exploit the selection policy. However, this still has very poor adaptability for different workloads and data schemes. So in summarization, the learning-based selection methods, they can outperform the heuristic partition methods, but has much higher partition overhead for model training. And the graph partition-based functions, they can outperform traditional functions like a simple range or hardship partition, but they still cannot work for some complex scenarios, like a partition for joint queries or large-scale data sets. So there are still many open problems like adaptive partition for relational databases, the partition quality prediction, which is especially important for learning-based partition selection methods, and how to improve partition availability with replicates for like on the small tables. Okay, let's enter the next section, the database optimizer. The first problem is the cardinality and the cost estimation, which is commonly seen as the heart of database optimizer. However, traditional methods are very simple. For cardinality estimation, is to estimate the size of the SQL query's results. They are based on the sampling or kernel-based methods, and they cannot accurately estimate the results. And for the cost model, histogram-based methods mainly model the data distribution of single columns and fail to work for multiple columns. And sampling-based model methods also have the performance degradation problem. For supervised query methods, they learn a mapping function between a query and its cardinality on the same databases. They treat the cardinality estimation as a typical regression problem in machine learning. They first train the query models with the sampled queries and their corresponding cardinalities, and then use the trained models to estimate the cardinalities of online SQL queries. To learn the cardinality of join queries, traditional join sampling fails to work when there are no suitable indexes or mid-severe sampling degradation. So one work just proposed a deep learning-based method that uses the linear models to encode different parts of circles, like the table, joins, or predicate features, and then they concatenate the different parts into an embedding vector. And finally, learn the network parameters to fit the mapping from the query features to the actual cardinalities. And another challenge is that there may be correlations between the multiple columns in the same table. Traditional methods, they just require to assume column independency, which may not work for this scenario. So learning-based method, they use a chain-based assembling algorithm to solve this problem. They first use the local neural network to encode different predicates on a fixed join path of the query. And since a query plan is a binary tree, they use tree-based assembles like a charge boost to pass the encoding vectors of the query through the traversal of multiple binary trees, and outperforms the average value as the estimated cardinality. Instead of assuming independence between the columns, these network parameters are used to fit the mapping of queries to cardinalities. Another class is supervised data model that learn the data distribution model based on some SQL queries and their real cardinalities. During supervised learning, they sample some data based on the query predicates and train the data distribution model to output the probability of the query ranges. And then in cardinality estimation, they uniformly sample tuples and use the data model to compute the cumulative densities of all the selected samples, whose sum up is taken as the estimated cardinality. So the first challenge is how to select a powerful distribution model that can work for so many rows in the same table. One work is to use a kernel density-based estimator for this problem. They first sample some rows from table and initializes the bandwidth of the kernel density estimator. And then it picks the optimal bandwidth via the stochastic gradient descent. Besides, Park also proposed a query-based method with maximum models. The maximum model is the probability density functions for fitting the observed predicates and the selectivities of predicates by minimizing the differences between the models and the observed distribution. They adopt two ways to represent the data distribution. The first is sampling based. The generates multiple random points, creates subpopulations on the points, and estimate the excess selectivity based on the maximum model learned from the subpopulations. And the second is cluster-based. On the sample data, it clusters the points based on the smallest rectangles that covers all the points, which may have more subpopulations to learn but has higher accuracy. This method can efficiently avoid the overhead of multi-dimensional histograms. However, it still cannot support some complex queries with lack or excessive keywords. And the last class is the unsupervised data models that can directly use the data to train the data density models. They first sample some reasonable amount of The last class is the unsupervised data models that can directly use the data to train the density model. They, for example, reasonable amount of tuples uniformly. And then they input the data tuples into the data model to learn the joint distributions. And finally, they sum up the cumulative densities of all the select samples as the estimated canality, like the second class, right? However, to learn the joint probability distribution over all the columns, the efficiently support the canality estimation for range queries, Yang has proposed to use the autoregressive density model to represent the joint data distribution among columns. The model returns a list of conditional densities present in the chain rule with an input tuple. To support the range partitions, the model adopts progressive sampling to select the meaningful samples by leveraging the learned density models. It works even with scored data. However, it cannot support high-dimensional data or multiple table joins. So, as we see, the deeper AI models can only handle single tables, and then we need to learn from join correlations. This method has solved the problem that it can be both the deeper AI model and the joint sampling method. First, it learns a single autoregressive model for all the tables. And second, the joint sampler provides correct training data, like sample tables from join, by using the unbiased join counts. Lastly, it downsamples some tuples from the lag table when estimating the query, with only a subset of tables, according to the Van Alten scaling. However, to learn the joins of all the tables, it can be very time-consuming, especially when the dataset is a bit large. So it is still challenging to estimate for the join queries with a poorly data-driven method. There are also some product network-based method. It mainly aim to solve the problem that some data in the tables may have different distributions, and they are independent from each other. So in this method, they first split the data table into multiple segments based on independency relations, and the columns in each segment are nearly independent. And then they build a relational sum and product network, where the sum is for the future operations and the product is for the joint operations. And to support the aggregates like average and the sum, they multiply the expectations of the aggregates with the probabilities coming from the child nodes. Another important problem is the cost estimation. So what's the different from the canality estimation? First, cost estimation is to approximate the execution time of resource consumption, where canality only talks about the resultable size. And the cost estimation is also based on canality in the traditional database of the measures. And the cost is much harder to estimate than canality estimation, because then it needs to consider multiple factors like sequence scan courses in the physical level. So there are relatively rural works in cost estimation. One work is to solve the problems in traditional cost estimation that can only use the estimated canality to further consider the cost, which is inaccurate without the encoding of query predicate. So Sun has proposed an encoding learning-based cost estimator with a tree-structured STM that learns a representation for each subplan with physical operators and predicates, and outputs the estimated canality and the cost simultaneously by using another estimation layer. Moreover, the method encodes keywords in the predicates using the word embedding. So in conclusion, for cardinality estimation, the data models are more effective for single tables. Query models are more effective for multiple tables because the sampling time for the data models are too time consuming. And query models are more efficient than data models, especially for the learning of data distribution model. And data models are more robust than query models because it only learns the underlying data distribution and work for different data or queries. And training queries are vital to the query models, and samples are crucial for the query models. And for the cost estimation problems, the estimators based on neural network are more accurate than the statistic-based estimators. And the statistic-based query model is the most efficient. Next, I see the plan enumerator. Traditional optimizer just relies on heuristics or dynamic programming to select high-quality query plans like operator selection and join order selection. However, the plan space is very large. A traditional optimizer cannot give a very high-performance plan within limited time. So there are two kinds of learning-based join order selection methods. The first one is offline. It uses existing workload to train a learn optimizer, and the learn optimizer will predict the plan for future workload. And another is online methods, in which the plan of a query can be changed during execution, and the query can switch to another plan if it finds a better plan, and it can learn when the database executes the plan. Two recent works have been proposed to use deep reinforcement learning to reduce the search space for offline learning. Similar to dynamic programming, we first model this process as a Markov decision process, and the optimizer is an agent, a join is an action, and the environment is the cost model or database. The reward is our cost or the true latency, and the state is our join order. The picture on the right describes the Markov decision process of the join procedure. In the beginning, we have the initial state of 4 independent tables. Each time we select the 2 tables to join, we got the intermediate state. After 3 join actions, we get the final plan, and this is the termination state. Moreover, the ball-tour methods cannot support updates on schemas. To address this problem, RTOS uses a 2-stage training to generate better join order on latency with a well-designed neural network structure. In order to address the problem of caching the structure of a join tree, RTOS proposes a model that utilizes the tree LSTM to represent the join state. The RTOS first designs the representation from column, table, and join tree. Then the DQN is used to guide the join order generation after the representation is obtained. Next, RTOS first uses the cost to pre-train the TNN network, and then utilizes the latency information to fine-tune the neural network online. And the experimental results and find that it can have a very high performance for different database schemas. Another class is the online learning-based methods. This class of methods focus on learning a join order using adaptive query processing, which can change the join order even during the execution. Anu has proposed an adaptive query processing mechanism called adding, which combines the execution and the optimization of a query. It learns and generates the join order during the online execution of a query. First, it displays the query process as many operators, like 2 join operators between 3 relations in this picture. And the adding uses 2 routing methods to control the order of this operator. like the naive, just greedy-based, and the lottery, the probability-based, will handle the incoming tuples. Besides, Trauma has proposed a Monte Carlo tree search-based method called SkinnerDB. SkinnerDB uses the MCTS instead of other reinforcement learning-based methods like Q-learning because it provides theoretical guarantees on cumulative regret over all the choices. And SkinnerDB divides the query execution into many small time slices, and in each slice, the chooses one join order to execute, using the real performance of a join order in the time slave. SkinnerDB changed the Monte Carlo tree search to get a better join order selection. And finally, SkinnerDB merges the tuples produced in each time slice to generate the final results. This table has summarizes different methods for join order selection and plan enumeration. And we can find that the learning-based algorithm usually gives the plan with low time complexity, especially for large queries. And the offline learning methods use the sample workload to pre-train the model. It will give very good plans for the incoming queries on the same data size. And a new database will lead to model retraining for both the offline and online methods. Online learning methods does not need previous prepared workloads and can give very good plans even for dynamic query processing. But it needs the customized engine, and it's hard to be applied in existing databases. So that's a key problem for online learning-based method. And there are many realistic open problems, like how to raise the generalization performance of offline learning methods for the unseen queries, and how to ensure the plan given by the learned model is robust, and how to speed up the model training time, like transferring the previous knowledges, and finally, how to make the model aware of the data updates. So let's first see the basic idea of learn index. Tim has proposed that all the indexes are actually models, where the B tree index can be seen as a model that maps each query key to its page. For a sorted array, larger position ID means a larger key value, right? And the range index should effectively approximate the cumulative distribution function, or CDF in short. Based on this observation, Crosscap has proposed a recursive model index, which uses a learning model to estimate the page ID of a key, and this method outperforms B plus tree under the in-memory environment for relatively small data size. However, they cannot support data updates, and it doesn't show the effectiveness for secondary indexes. So there are still many challenges for practical learning-based indexes. First is how to build a multi-dimensional indexes. We know that to utilize a multiple dimension index, we need to decide which columns are accessed together and carefully arrange their access orders. And the second challenge is how to support updatable indexes, like inserts, deletes, or updates that will severely modify the data distribution, which require learning-based index models to support dynamic data modifications. In this taxonomy, we can see that current learning-based methods can be divided into immutable learning indexes and mutable learning indexes. For the immutable learning indexes, there are one-dimensional index like MI, which is a hierarchy architecture where each model picks another model based on the input keys until the final stage and predicts the position. And there are also multi-dimensional indexes like a float, which models each attribute using the recursive model index just as the RMI in the cell divided by the optimal layout. And for the mutable learned indexes, there are fixed data layout index like a lex, which dynamically adjusts the shape and the height of the RMI index depending on the workload to provide more robust performance even when the data distribution is good or dynamically changed. And for the time limit, you can find more details in the related tutorial in SIG Spatial 2020. We just do not give more details here. And another problem is how to design more complex data structures, since traditional data structures like the secondary indexes, hash map, blue filters, they are also unaware of workload or data characters. So instead, we can reconstruct the data structures for higher performance. In the learned KV storage design, Addressor has shown that data structures in key-value storages can be constructed from fundamental components, and the learned cost model can guide the construction directions. They define the design space as all the designs that can be described by fundamental design components, such as fence pointers, links, and temporal partitioning. And design continuums is a subspace of design space which connects more than one designs. To design a data structure, the phase first identifies the bottleneck of the total cost, and for which the model can be tuned to leverage it, and then tune the knobs in one direction until they reach its boundary or the total cost reaches the minimum. This process is similar to the gradient design in machine learning and can be conducted automatically. So in conclusion, the learning-based method opens up a novel idea to replace traditional data structures like an index and show good performance in small data sets. And the learning index uses machine learning techniques that can provide the probability to combine the new hardware. And though some research has already verified the benefit of learning indexes, the performance in industrial level scale still need to be studied, especially in updatable and multi-dimensional situation. And there are still several open problems, like how to support learning index in distributed system, and how to support more large data scores, and improve the stability of learning indexes. Next, we'll introduce transaction management. The motivation includes that you need effective transaction scheduling, and that can significantly improve the performance by minimizing the resource or data conflicts between different transactions. And it's challenging to control the concurrent queries or transactions. And besides, for the transaction management, there are different cases like transaction prediction or transaction scheduling. First, for the transaction prediction, it's important to database optimization like resource control or the following scheduling tasks. While traditional workload prediction methods are rule-based, they just identify the signals like internal latency or resource utilization in the database that are relevant to the workload characters, and builds a statistical model for the workload prediction, which can consume much time. So Ma has proposed a learning-based method to predict the future trend of different workloads. In the first part, it identifies the query templates and the arrival rate from the workload, and then it combines templates with a clustering-based algorithm based on the arrival rate patterns, and finally, the well-for case, the arriving rate of the new queries based on the clustering method. Another work is transaction scheduling. Traditional database systems add schedule workloads sequentially, which cannot consider potential conflicts or schedule the workloads based on the execution causes predicted by the database of the method, which may be very inaccurate. So Zhang has proposed to learn to schedule queries to minimize the disk access requests. It first collects some the state of the request data blocks from the buffer pool, and then it will featureize the state features like buffer pool size and the data block requests. And finally, it just schedule the queries to optimize the global performance based on the state features with the IR method like Q-learning. After that, we will introduce and we can see that current transaction, and we can find that we can use the deep learning for the transaction management. Mini has two observations. First, for the transaction prediction, simple neural network cannot efficiently support concurrent query features that have complex correlations. So they just propose some more complex models like a clustering-based or the graph embedding-based. And for the transaction scheduling, they still use the classical reinforcement learning-based method to optimize the policies. So we have two observations for the transaction management. For the transaction prediction, we can see that simple neural networks cannot efficiently learn the correlations or the patterns. So there are the methods like RNN or more complex the graph embedding method. And for transaction scheduling, they still adopt the classical reinforcement learning model to optimize the policy, but it is still time consuming for the exploration process. Next, we will introduce the self-monitoring and the diagnosis part. For an autonomous database, generally, they collect performance-related metrics like resource utilization or L metrics, and detect abnormal metrics and diagnosis corresponding root causes. This is the whole circle of the self-monitoring and the diagnosis procedure. So the first problem is how to proactively detect the database performance. There are works that predict performance changes, especially for the concurrent queries. The traditional prediction method only captures the logical L metrics and neglect many resource-related features and cannot get very accurate results. So Marcus has first proposed a deep learning-based model to predict the query latency and the concurrent scenarios, including the interactions between the child parent operators and the parallel plans. However, they just denote the child operators and the parallel plans as the tree nodes and cannot capture the operator-to-operator relations like data sharing and conflict features. So Joe has proposed a performance prediction method with graph embedding. They use a graph model to characterize concurrent queries, where the vertices are operators, the edges capture the operator correlations like data parsing and axis conflicts. And they use a graph convolutional network to embed the workload graph, extract performance-related features from the graph, and predict performance based on the features. After detecting the abnormal performance of metrics, next we need to diagnose the root causes. There are three motivations. First is that the system performance problem is very common, especially on the cloud databases. And traditional diagnosis highly relies on DBAs and experts, and is very costly and time-consuming. And AI methods can utilize historical data and rules to enhance the diagnosis procedure. Based on the workload types, we can divide existing diagnosis workloads into RTP-oriented and lab-oriented. First, for the system diagnosis for RTP, the meaning takes the whole workload into consideration. One method designs a machine learning algorithm to extract abnormal metrics and utilizes a causal model to diagnose the potential causes. They collect the statistics and merge statistics based on the time step and then explain the root causes with the causal model, where each root causes is a cause variable with several effect predicts like the CPU weight, latency, and the disk write. Another approach is also based on DBA's experience. They assume that some slow queries with similar key performance indicators have the same root causes. They adopt a two-stage diagnosis. In the offline stage, they extract slow queries from the failure records, cluster them based on the KPI state, and ask DBAs to assign the root causes to each cluster. And in online state, for an incoming slow query, they match it to a cluster based on the similarity score of the KPI state. If matched, they use the root cause of the cluster to notify DBAs. Otherwise, they generate a new cluster and ask the DBAs to assign the root causes. However, this method cannot prevent potential database failure. So another method is system diagnosis for lab. Queries in analytic workloads are parallelly executed, which can be modeled as a DAG of stages. So is to compute the resource contention between the queries and the causes of execution slowdown. In this method, they first build a graph in multiple levels, like a query level, resource level, and a server level, and it detect the victim queries and explain the causes of the victim queries by traversing a path in the DAG from some nodes in the level 6 to the victim query. Another interesting solution is to unify the diagnosis on database like a PostgreSQL and the SAN storage. The core idea is to build a knotted plant graph from the workflow of the query execution. The first builds a graph by parsing the query plans as a tree, and then it will correlate the operators in the SAM model with the nodes in the tree. And then it will compare the newly built tree with the historical data and judge whether the query plan has changed and which operators consume much more time. And finally, the will analyzes the operator correlations and judge the important operator size. And finally, the will diagnoses the root causes based on the important operator size by matching with previous problems that cached in the knowledge base. Yes. So in this table, we can summarize the differences of the different system diagnosis methods. And there are some more general for both the RTP and lab workloads diagnosis methods in the commercial databases like Oracle. However, all of those methods, they are knowledge-based, and the most current methods are not very efficient in using the DBS expert and the machine learning techniques. So in summarization, load monitoring works better and can largely reduce the problem detection latency and save the manpower. And the current learning-based monitoring method still needs DBS to decide the key metrics, and they cannot automatically decide which metrics are important in different scenarios. And learning performance prediction provides more accurate execution information than cost estimated by the database optimizer because they can consider more execution-related features and the correlations between the physical operators. And since different databases may have different execution mechanism, it is extremely difficult to migrate the learn of the monitoring methods to different databases. And most existing diagnosis works rely on experiences, and we need to some further knowledge and insights to combine the expert experiences and the machine learning techniques. So there are actually many open problems like diagnosis on low cost and they to obtain statistical metrics. And we need to diagnose for parallel transactions like D-trace. And finally is the data security. We can find that there are different aspects that are very important in database security. The first is sensitive data discovery. Since the leakage of sensitive data can cause great financial and personal information loss, it's important to protect the sensitive data in a database. However, traditional methods use user-defined rules. With learning models, we can automatically learn the real access frequency of data records. And the second issue is access control. It aims to prevent unauthorized users to access the data, including the table level and the record level access control. However, traditional methods are based on static rules. With learning models, we can customize policies to regulate the data requests based on both actions and the data access patterns. And the final issue is a SQL injection, which is very common and harmful to databases. Attackers may modify or view data that exceeds their priorities by passing additional information. Traditional methods take a very long time in scanning SQL injection. With a learning model, we can classify different SQL injection actions and use techniques like fuzzy networks to automatically learn the attack patterns and prevent SQL injection. Finally, we will introduce some more autonomous systems that integrates the above learning-based techniques in databases. There are several motivations for the autonomous database systems. First, traditional database design is laborious. We may need to develop both the system and the data structures based on the access patterns. Otherwise, the general modules may not work well in other cases. And most AI4DB works only focus on single modules, which can cause local optimum. Besides, there are some commercial practices of AI4DB works, and we can find that the heavy machine learning models are hard to implement inside the database kernels, and a unified platform is required. So the first vision is Peloton that Paolo just proposed to predict the workload arrival rate with clashing RN and deploy the optimization actions based on prediction results, and they can optimize databases with actions like knob tuning or index or machine learning materialized view selections. And the SecDB has also proposed a vision to specialize the database implementation by learning the data distribution, like learn the CDF models and designing the database components based on the expert knowledge and the CDF models, like the learn index, or the query scheduling, and other physical operator optimizations. Since about two did not implement in the real scenarios, Lee has proposed the OpenGauss, an autonomous database system that validates, trains, and implements state-of-the-art learning-based components in an open-source commercial database. They build an autonomous database framework and integrates their proposed learning-based database techniques into the open-source database system, like the learning-based query writer, the cost estimator, and the plan enumerator. And for the outside maintenance, they also support self-monitoring, self-diagnosis, configuration, and optimization. Besides, they also devise an effective validation model to validate the effectiveness of learning models. So in conclusion, AI can solve many tricky issues in databases, like high-dimensional regression and NP-color problems. And AI can help to automate database optimization and maintenance, especially on the cloud. And besides, current AI4DB was mainly focused on overlap workloads, where data is rarely updated and users are not sensitive to the training latency. However, for OLTP, the data may be frequently updated, and users may require very high model inference efficiency and robustness, which are great challenges for current AI techniques and requires more system and algorithm designs.
Hello everyone, my name is Chenliang Chai from Tsinghua University. Then let me give a talk about the DB4AI overview, including the motivation, framework, and some fundamental techniques. So let's first talk about the challenges in machine learning. First, the machine learning models definitely need high-quality training data. However, it is always expensive to hire experts to acquire or label sufficient data. Second, a large number of training data naturally makes training less efficient. Besides, many typical model structures are becoming larger and deeper, especially for deep learning models. So this makes the machine learning pipeline more inefficient. Third, model training is not a one-shot process, and data scientists always train iteratively, test many models, and select the most appropriate one. But these trained models are hard to manage because they incorporate too much information. Hence, how to manage these models and the corresponding data artifacts remains a challenge. To address this challenge, both DB and machine learning communities propose an end-to-end data analysis pipeline, where many DB techniques can be utilized to benefit the effectiveness and efficiency of the machine learning tasks. We discuss relevant techniques from these three aspects along with the machine learning pipeline. First, the pre-ML, which is also named by data preparation, is needed for preparing high-quality training data, including data discovery, cleaning, and labeling. Secondly, model training consists of a number of time-consuming steps, including feature selection, model selection, as well as training and inference stages, which can be accelerated using DB techniques like materialization or parallelism. Thirdly, DB-based techniques can always be used to manage the trained models, including model storage, query, deployment, and debugging. Thus, the above steps have been extensively studied recently, and we review them thoroughly in this tutorial. We first talk about the data preparation. As reported by Forbes, data preparation accounts for about 80% of the work of the data scientist. Also, as discussed by Google, machine learning code is less than 5%, and other parts including the data collection, feature extraction, serving infrastructure, or monitoring. So let's first talk about the data discovery. Data discovery aims to retrieve training data related to the machine learning tasks from external resources like the web, data warehouse, or data lake, which is the first step in data preparation. However, In real scenarios, usually only a small number of data is available, lacking attributes, tuples, or features. To address this, many researchers have started to discover more data for better model performance. In this part, we categorize the data discovery as attribute or tuple level and table level data discovery. The goals of data discovery are as follows. The first, items in a table should belong to a specific domain, so we may hope to discover as many items as possible in the domain. Second, we expect that the discovered entities or tables should be integrated into the table. That's about accuracy. Thirdly, most time there are a large number of data in external resources. The efficiency is another problem. The last one, most methods only consider fetch more related data without considering whether this data can improve the downstream model. So let's see the table about the comparisons of data discovery. The first column is the category, and the second column refers to that whether it can benefit the machine learning model or not. And the second column refers to the method. And the first column denotes which model the machine learning oriented method can benefit. And the source column refers to where we can discover the data. Then let's see how to discover new items or attributes. First, let's see the data-oriented method. We talk about discover from the surface web, discover from the hidden web, and discover from humans. First, let's see the info gather. So suppose we have a query table, namely the base table. InfoGather leverages a vast corpus of HTML tables on the web to discover the missing cell by attributes or several examples. And it can also discover attributes by the cell values. The basic idea is to first identify the web tables that have matching schemas with the base one, but it always suffers from the low accuracy and coverage. So the InfoGather proposed a holistic probabilistic method that considers multi-hops relations of tables to conduct the value inference. Then let's discuss how to discover from the hidden web. The smart crawl aims to discover from hidden web by querying APIs like Yelp and DB4AI. For example, we want to discover the rating attribute of the restaurant by querying the Yelp, but the number of query is limited or the query is not free. So the optimization goal is to reduce cost, which is the number of the queries while discovering more complete items or attributes. For example, we can submit a very specific query like the Thai noodle house. So we can retrieve an accurate rating, but the number is always limited, say only one. We can also submit a general query like the type. In this way, we can query more, but some of them may be useless. So there is a trade-off. So let's see the pros and cons of the discovery from the web. The pros are that first, the automatic methods. They are automatic methods with high efficiency. And concretely, the surface web. It considers different HTMLs holistically with low cost, which can fill both tuple cell values and attributes. And the hidden web always clean and accurate, where user-friendly APIs can be used. And the cons are as follows. These methods do not consider much semantic information, and long-tail cases are not easy to cover. For surface web, the data is always dirty, and for hidden web, the data is clean but costly. Then let's consider how to discover from the crowd. The crowd field aims to discover from the crowdsourcing, which provides user-friendly interface for workers to collaborate on the web. For example, the worker can retrieve the fresh entities, the whole entity, or the missing cell values. And the workers can also vote for each other. So the crowd EC also aims to discover from the crowd, but the difference is that it has a more fine-grained optimization goal, including the quality, cost, and completeness. The quality means that we should discover items belonging to the domain. For example, if we want to collect the NBA players, and if one provides a soccer player, it is wrong. And also, we hope the workers to provide distinct entities, because if many workers provide duplicate entities, we should pay them, but it is wasteful. So there are two models. One is a worker elimination, which eliminates low-quality workers to improve the quality, and the other one is incentive pricing. We provide bonus to encourage workers to provide distinct entities to reduce the cost. And the pros and cons are listed as this. The pros are humans can provide semantic aware items, and they can check for each other with high quality. And the important one is that the long tail cases can be discovered more easily by the human intelligence. And the cons are the crowd workers have high latency, so it is not so efficient. And the crowd is not free, so they cost too much, but the cost control techniques can be applied. And the quality should be carefully controlled, including the distinctness. And then we talk about the machine learning oriented, which considers the downstream machine learning model performance. The above method just enrich data set without considering the performance improvement it follows. So this method, the auto-augment focuses on the image data rather than the tabular. So for image data, they have many augmentation operations like flip, rotate, scale are always applied to enrich the training data for performance improvement. Auto-augment uses reinforcement learning to search a sequence of optimal augmentation operations automatically. Specifically, each policy defines which operations to use and the probability of applying the operations in each batch. The agent first predicts a policy from the predefined search space. Then a child network is trained to achieve certain accuracy after applying the policy. Finally, the accuracy is regarded as a reward to update the prediction strategy in the first step. And the pros are the automatic and efficient discovery without human involved. And the second one is that the method cares about the machine learning performance in iterations. And the cons are just the auto-augment just discovers from the training set rather than involving real fresh data. And this method is limited to images but hard to structure data or text. Then next, we introduce the table level method, which focuses on discovering tables based on the user requirement. So GOOD is a table-level method which manages the data in the data lake and provides an interface that allows users to explore the tables. Specifically, it stores information like a dataset schema, similarity, and provenience between datasets. Users can search and browse datasets using the keywords. However, such systems have limited usage in ML because they cannot support to search related datasets given a query dataset, which is a common requirement when current data is not enough. To this end, the algorithm is proposed to use a graph-based data structure to discover data. It provides flexible queries to query the dataset based on the user request, so that one can find candidate dataset to join. Based on the database meta information and a given ontology, our rule matching the database and references using embedding methods based on which relationships between tables are established. Thus, highly related table can be found and the link can be propagated using the transitivity to find more tables. However, the above methods do not consider the downstream machine learning model. The pros of these methods are they provide user-friendly interface and users can query the desired tables easily. And they can manage the large number of heterogeneous datasets in the data lake. And we can also recommend more related tables besides the query table. And the disadvantage are that they just rely on the external reference to link related datasets, and they discover tables that only have similar semantic meaning without considering the machine learning performance. Then we come to the Helmet project. It answers the question that whether the foreign key joins between the base tables and tables in the data warehouse are necessary with the goal of improving the performance of the machine learning model. If not, some tables in the data lake can be proved in advance without drawing and training, so that the efficiency is improved. The basic idea is that the foreign key in the base table has been encoded enough information of candidate tables. For example, suppose that the base table is customer and one of the candidates is employer, so they can be joined through the movie ID. So since many customers might see the same movie, so it is reasonable to use movie ID as a feature directly, rather than drawing the two tables. Specifically, Helmet proposed a measurement called the risk of representations, which is ROR, that leverages the VC dimension to compute the difference of the train and test errors of the machine learning model if the drawing is avoided. So the higher the ROR, the drawing will be more necessary. Otherwise, one may consider to drop the candidate table. However, this method is limited to models like naive Bayes and logic regression with VC dimension linear to the number of features. So ADA is another machine learning-oriented data augmentation framework that discovers tables from the data lake, so as to improve the performance of the downstream machine learning model. Unlike the previous Helmet, it supports fuzzy join with data from data lake. So one can conduct this using the brute force approach which is drawing the base table with all related tables and then conduct feature selection. But the drawing is always time consuming. We can improve the efficiency through two aspects. One is to reduce the size of this base table, and the other one is drawing fewer tables. So ADA leverages these two ideas. So therefore, ADA samples some representation tuples using into simple heuristics from the base table when the base table size is large, and utilize these samples to learn the augmentation plan. Then they conduct a step-by-step fuzzy join. It further improves the efficiency by drawing the base table with the candidate table step by step rather than drawing all of them together. First, it sorts the candidate table based on their relevance to the base table. This can be done by the OR. Then it draws the table step by step based on the ordering. In each step, the other feeds a batch of tables to join with the base table considering the trade-off between storage overhead and efficiency. And then they conduct feature selection, train the models, and test the accuracy. When the accuracy does not increase or a predefined budget of steps have been achieved, the augmentation process terminates. So the pros are It considering the model performance. The join tables can improve the model performance, and they support both PKFK and FADI joins. And some acceleration techniques are proposed, like sampling and join step by step. And the disadvantage are that the join is still time consuming because there still exists a large number of candidate tables. And the second is that the loss of missing values can appear because not all items can be joined. So here is a takeaway of data discovery. Data discovery enrich the tuples, attributes, or features of the dataset, aiming to improve the quality of the machine learning performance. But not all methods can directly improve the machine learning models. These methods just consider to enrich the dataset, discover more tables, more attributes, or just the table can be union or join. They do not consider the machine learning performance. So besides the performance, the efficiency is another significant concern because there are always a lot of tuples or tables in the data lake that we cannot train. So we always use join, which is very inefficient. Let's talk about the data cleaning. So the data retrieved from the external resources is always dirty. So data cleaning is always applied to detect and repair the dirty data. So the US government reports that the dirty data results in a total loss of US dollar about 600 billion a year. So there are many types of dirty data, including the inconsistency, duplicates, outlier, missing value, mislabels. So there are a lot of tutorials and surveys talking about the data cleaning, how to detect, where to detect, and what to detect dirty data. But in this tutorial, we focus on the problem that do we need to clean all types of dirty data for the machine learning? And the answer is no. So the motivations are that the different type of dirty data have different impacts on the machine learning models, and different data items also have different impacts on machine learning models in a more fine-grained way. So the challenge is how to identify them to avoid unnecessary cleaning operations, because data cleaning is always expensive because it always needs humans' help. So we first use a table to overview this. So here, the clean ML is a benchmark for joint data cleaning for machine learning. It tests the impacts of these data errors on 7 typical machine learning methods like multi-regression, decision tree, and random forest, so on and so forth. To summarize, we draw a table to illustrate the relationships between data errors and the machine learning performance. So the column positive means that whether the cleaning contain errors has a positive effect on the model. And the negative column denotes that whether the cleaning operations has a negative effect on the model. And the model selection denotes that whether the model selection can promote the positive or eliminate the negative effects. And we can from the table that the first row indicates that the second row indicates that the cleaning duplicates will degrade the model performance because the data distribution may be changed. But the degradation can be eliminated by judiciously selecting models. So for another example, cleaning the outliers may have positive or negative impacts on the machine learning tasks, which highly depends on the specific machine learning task or data size. So what's more, making the data more consistent is not likely to influence the model, but the model selection increases the probability of having positive impacts. And verifying mislabels and imputing missing values have positive impacts on the machine learning tasks. So let's see whether cleaning certain items have impact on the machine models. Then let's see a concrete method about data cleaning for machine learning. First, the active clean. It first justify whether we need to clean the data to obtain a well-performed model. So from figure E, so this cross denotes the dirty data. There are 5 data objects, and the green ones are the clean version of this cross. So we can see that we train 2 models, they are so different. So this figure shows that the cleaning is necessary for the machine learning task. And the second figure answers the question that whether we can just clean a part of data and then train a model. So the answer is not. So for example, if we just clean the 4th and 5th data objects, and we can see that the red line and the blue line are still very different, and they are so the model cannot perform well at the blue line, the blue model. So we cannot do not clean, but we also cannot just clean a part of data. So then whether we can just clean a part of data and produce a high quality label, the answer is yes. So at a high level, the reason why the dirty data degrades the performance is that they mislead the gradient computation. Then if one can clean part of dirty data, compute the variations of the gradients, and estimate the gradients of the uncleaned data, and they can quickly converge with a small number of clean data. So active clean consists of 4 models, which are sampler, cleaner, updater, and estimator respectively. The sampler is utilized to select a batch of records to be cleaned, where the selection criterion is measured by how much improvement can be made after cleaning a record. That is the variation of the gradient. The improvement is computed by the estimator based on the current cleaned data. Then the selected record will be checked and repaired by the cleaning, which can be conducted by humans. Next, the updater updates the gradient of the entire dataset based on the verified dirty data. And these 4 steps iterate until the budget is used up. So there is another work called boost clean, which aims to clean the data where an attribute is out of range. It takes as input the dataset a set of predefined functions for detecting and repairing out-of-range values, as well as a black box model. These values will definitely degrade the model performance. So the optimization goal of the boost clean is to explore the best sequence of the repair operation so as to best improve the model. Rather than constantly enumerating every record in the original dataset and clean it, it makes the observation that detecting errors and applying a cleaning function on a dataset can be seen as generate a set of new features, and then a new model can be trained on the cleaned dataset. So they use the boosting idea, which views each repair operation as a weak classifier and combine many of them collectively to make predictions. To be specifically, in each training iteration, it first generates the best classifier on current dataset and weighs the dataset considering the missed predictions by current classifiers and repeats the above step until the budget is used up. So the CP clean focus on the reasoning about the impact of missing values on downstream machine learning tasks. We suppose a dataset has n missing values and the domain set is m. We have m exponential n possible imputations. So all the imputations consists of a possible word, and each of them corresponds to a model. We hope that the predicted label of all models are relatively consistent for each tuple, so that the less cleaning operations are necessary. So an ideal case is that all labels are the same for an example. And this example is called the certain prediction. Intuitively, if all test examples are certain practice, it is wasteful to impute the missing values. Therefore, the optimization goal of CP clean is to prioritize imputing the record that are likely to make the test examples have consistent labels. That is supposed to be certain predictions. So a straightforward method is to train all the models and make predictions, which is too expensive because training is inefficient and the possible world is extremely large. So CP clean addresses this problem by restricting the models to KNN classifier in this way. To compute whether an example is certain practice, we only need to consider the similarity score between the example and the training data rather than training the models. Then the DA GAN also focuses on the difference of the distribution of missing values on multiple attributes between training data and test data. This often causes the performance degradation on test data, and it is a common scenario because a single trained model is likely to be used in different test cases with different missing value distributions. To address it, the basic idea of DA GAN is to reduce the divergence data distribution between training data and the test data. The key idea is to capture the missing value distribution from the test data using GAN, and it adapts the training data to capture the distribution without changing the labels. After that, it refines the machine learning model by retraining with adapted data. So here is a comparison of data cleaning, and the first column is method, and all of them focus on improve the model, and they use different method, and some of them are automatic and some are not because need human, and they clean missed values, outliers, some of them, and they follow different model types. So the pros of these methods are that the data cleaning for machine learning, considering both both the data and machine learning algorithm. And these methods save much cleaning costs because large volume of unnecessary operations are saved. And the cons are that the data cleaning always needs much human effort. And the existing method always restricted to error types like just outliers or missing values, and some of them also restrict to the machine learning models like convex models. So here is the takeaway. So data cleaning aims to detect and repair data errors, but not all the cleaning operations can directly improve the machine learning models. And some may even have bad impact like the duplicates. So cleaning directly for machine learning always focuses on looking into the machine learning algorithm and finding the close relationships between data and the algorithms. So it's very interesting and important. Then let's talk about the data labeling. So we categorize the data labeling into three groups. One is the crowdsourcing. It leverages the crowd intelligence to label the data. And the second one is active cleaning, which hires the high-quality experts to label. And the final one is weak supervision, which leverages the rules and imperfect labels to directly train the model. So here is the comparisons of different data labeling methods. So we compare them through the data label quality, label cost, and label latency, and whether it is for the machine learning. So the crowdsourcing leverages the human intelligence to install the tasks that are hard for the computer, like labeling in the machine learning. So it consists of the three parts. So the requester, submit tasks, and the crowdsourcing platform like Amazon Mechanical Turk published the tasks, and the workers find interest tags, return answers, and the requester collects the answers. So the challenges in the crowdsourcing are threefold, and they have trade-off. First, the cost. The crowd is not free, so we should reduce the monetary cost by some pruning techniques and some deductive strategies. And the second one is the quality, and because crowd may return incorrect answers because there may be some low quality workers. And the third one is the latency, because the crowd is not real time. So there exists trade-off between these three factors. So, for example, if you want to improve quality, you may assign your task to multiple workers, and so the cost is large. So the pros of the crowdsourcing method is that a large number of intelligent workers you can hire. So thanks for the crowdsourcing platforms like AMT, we can hire workers very easily. So the disadvantage are that crowd workers are error-prone, so you need to improve quality. And crowd workers are not free, and this method is not directly for the downstream models. It just generates the labels, and then you aggregate their answers and inference the final labels, and then you use these labels to train the model. So it's not direct. And the second one is active learning. So it is a widely studied work, and there are many tutorials and surveys you can refer to. So we just generally say something about this. So first is uncertainty sampling. It's very simple. We just use entropy to measure the uncertainty. And the second one is query by committing. So the basic idea is similar to the previous one. It's just you can just test multiple models and use the uncertainty of the multiple models to select the data objects you need to label, and and then following the expected model change, it selects example that would introduce the greatest change to the current model. So the change is measured by the gradient. So and the last one is similar to the third one. It measures the generation level is likely to be reduced of certain example and choose the example that can reduce the generalization error most. So the pros of the active learning are that experts are always high quality, and it is directly for downstream models because in each iteration, the active learning checks the relationship between data and the models. And the disadvantage are that experts are always very expensive, and it needs high latency to label this data. Then we come to the weak supervision. So the first part is learning from imperfect labels. So for crowdsourcing, it also generates many imperfect labels, but you have to so given one object, you ask five workers to label this, and you get 5 answers, and you infer based on that. But so the learning from imperfect labels, so this method is just train from these imperfect labels. The given the observed training data D, and they directly estimate the weight factor, estimate the quality of the worker, and infer the classification of each instance. So they can use the EM algorithm to conduct this. So then the other one is data programming. So many machine learning applications need a large number of training data, which is very expensive to obtain, even resulting to the crowd workers. So data programming techniques have been proposed to generate a large number of weak labels using multiple labeling functions rather than labeling for each example. So where each function can be written by humans. Naturally, a single function is far from generating high-quality labels, so multiple functions should be combined to generate labels. So the most straightforward method of combination is majority voting, but it does not consider the correlations and the qualities of different functions. So to address this, the Snorkel is proposed to aggregate the results of multiple labeling functions to infer the final labels. So with specific Snorkel, first provides a user-friendly interface and ask the experts to provide the high-quality rules. The labeling function, applying this function to data given a labeling matrix L, and this and then use this rules to build a fact graph. So L denotes the labeling function and N denotes the new labels, and they use a graph model to deduce the final labels. So that's the general framework of the data programming. So given some unlabeled data and some weak supervision sources like human provided rules, and we generate a label matrix and use a fact graph to build a model on these rules, model their relationships, and then they build a deep neural networks to directly use these labels to train a classifier. So the advantage of weak supervision is that it achieves both low cost and high quality due to the rules and models built on the rules, and it directly follows the downstream models. And the disadvantage is that the rules should be carefully designed by experts. So if the many rules are not applied, so the quality is horrible. And the second one is that more theoretical guarantees should be provided for the weak supervision. So the takeaway of the data labeling, so the data labeling always introduces trade-off between quality, cost, and the latency. So the one of typical labeling method is crowdsourcing, which is cheap but low quality, and the active learning is expensive but high quality. So recently, weak supervision is a good choice for achieving high quality but with low cost, and it is directly for downstream machine learning. Then let's talk about the in-ML field top up the feature selection. So let's see the comparison of feature selection. There are two main goals. First is for model quality, and the second one is for model efficiency. And the first one is always conducted by machine learning community, and the second one that we focus on is done by DB community. So since the model efficiency does not influence the model quality, so we just care about the efficiency in the second part. So first, let's briefly talk about the feature selection methods in machine learning community. So totally we divided it into three parts. So the first is filter-based method. It separates the feature selection from the learning algorithms. So we do not need to train anymore in the feature selection strategy, in the feature selection process. So the second one is wrapper-based method. It considers the predictive accuracy on select feature subsets. So the main idea is to enumerate many subsets and select the best ones by continuous training. And the third one is embedded-based method. It embeds the feature selection into the machine learning model, like the tree model, GPT, or the deep learning model. So in general, the DB-based techniques can be used to accelerate feature selection. So we mainly focus on the wrapper-based method for acceleration. So the first technique is batching. So the wrapper-based method is defined as follows. So given a set of features, so we aim to select the optimal subset that achieve the best performance. So the challenge is that there are a number of possible subsets have to be tested and loaded many times, which incurs much I/O cost. So the key idea to solve that is to batch some subset together and evaluate them in one table scale. So given the problem is as follows. So given a memory constraint S, so each subset Fi has a memory constraint. I have a memory requirement MF for training. For example, the F1, the subset F1 may have a memory requirement M1 and F2 has a requirement F2. So different subset have different requirements. So totally we have a memory constraint S and we aim to batch some subset together and evaluate them in one table scale. So the optimization goal is to minimize the number of table scale, which is an NP hard problem. So even if we have a batch technique, we have another challenge is that we have to load each batch via table scan and then evaluate, which is still example. So we can use materialization technique to materialize some batches of tables to reduce the read cost. So the key motivation is that each batch has different frequency to be loaded. So the problem is to select an optimal materialized solution where MI is a materialized batch. So this considers the materialized cost of the batch and the I/O saving of the batch. So this is trade-off. So we can also see this problem as a machine learning pipeline. So each machine learning pipeline can be regarded as a DHE graph. It starts from loading the data and conduct feature engineering for each attribute, which includes the extract feature, so make the feature into bucket and so on and so forth, many operations. And in the typical machine learning pipeline, we have to do this in iterations because we have to we have to add features, delete features, and tune the hyperparameters. So the intermediate result can be materialized to, for example, we can materialize the each bucket that these results, and so in the next iteration we do not have to rebuild this pipeline. So it is also it can be also solved by a materialization idea. So it considers the rebuild cost and the materialized cost. This is a trade-off. So the other method is active learning. Use active learning to do feature selection. So the challenge is that the model training, for model training, the convergence takes time. So it clusters the data items in the training set and uses active learning based method to select the high utility data for training. We can see from the graph, from the figure, that this method converges very early than the baseline. Next, we talk about the model selection. So model selection aims to select optimal model structures or hyperparameters. So the goal is to improve the model performance and the model selection efficiency. So let's first talk about briefly the model selection method in the machine learning community. So it consists of two directions. One is the traditional model selection, which selects from traditional models like SVM, random forest, KNN, so on and so forth. And the other one is the neural architecture search in AIs. This is for deep learning model, including the model structures and hyperparameter settings. So the DB-based parallel techniques can be used to accelerate the model selection, and that's our focus in this tutorial. So here's the comparisons of in parallel model selection method. So there are different methods, and they care about different optimization goals. So first, we care about the high throughput that means so we can test how many we can test how many model configurations in parallel, and then we care about the high scalability and how much distance we can test, and then we want to ensure the good convergence, and then we want to guarantee a good reproducibility. We want that the first running of the model selection and the result is the same as the second one and third. So the first is the task parallel. So the challenge is that the model selection needs high throughput. So current machine learning system focus on training one model at a time. So this method tests different training configurations on different workers in parallel. So the key idea is they copy their data to multiple workers and run different configurations in parallel. So the drawback is apparently it's needs high storage cost, so the scalability is low. So that another challenge appears is the high scalability. So the BSP addresses this challenge by partitioning the dataset across workers and train one model in parallel on multiple data partitions, and they average the model parameters and achieve the final models. But the drawback of it has poor convergence. So to address this convergence challenge, so the parameter server is proposed. It can be taken as a fine-grained way of BSP, which also runs each configuration in parallel. The difference is that the worker nodes send the updated gradients when each mini batch is finished and then pull the latest model from the master node. So there are two classes of the parameter servers, synchronous and asynchronous. And the former one asks the master to compute the average updated gradient when all workers finish a mini-match. So the latter one asks the master to train whenever an update occurs. Therefore, the asynchronous parameter server has a good scalability but poor reproducibility. Besides, the synchronous parameter server has better convergence because of the fresh gradient updates, but higher overhead due to the synchronization. Compared with the BSP, overall parameter server has higher scalability and better convergence because of its finer granularity in mini-batch, but the communication cost is higher due to the frequent communication. So to achieve high communication efficiency, so the model hop parallel technique is proposed. It combines the idea of task parallel and BSP to run configurations in parallel on both task and data level. So they remove the master node and they conduct the model hop between each partition. And given a data set, a set of model configuration to be executed, it first shuffles and partition data set, and different partition will be distributed to different worker nodes. And since there are multiple worker nodes, so this method evaluates the multiple configurations in parallel. So in each training epoch, it selects P models from S to train using the SGD and different partitions. After that, each model will hop to the next work node in accordance to the pre-generated hop schedule. So after several hops, all the model will be trained over the entire data set. So let's see the takeaway of the feature selection and the model selection. They are both hot topics in machine learning studied for years, which influence the model performance a lot. And then fortunately, they can be accelerated using the DB-based techniques like batching, materialization, and parallelism. So the above method accelerate the feature selection, model selection stages without training of the model. Then let's talk about how to accelerate the training phase while computing the loss and the inference stage. So we talk about this topic from 4 aspects, from the low level to high level. The first is the expression level, which uses the linear algebra optimization to accelerate the loss or gradient computation. And the second one is the table level. So it's called the factorized IML. This because the machine learning algorithm always involve multiple tables, and they need to join, and join is always inefficient. And the third one is the computation graph level optimization, which optimizes the computation graph in the deep learning. And the last one is hardware acceleration. So let's first look at the linear algebra optimization. So the motivation is that most machine learning algorithms relies on the linear algebra. So rewriting a linear algebra expressions can greatly reduce the execution time. So we categorize this topic into 3 parts. First one is in database linear algebra optimization. So this work is proposed to execute the linear algebra operation into the base so that the computation of these operations are likely to be accelerated because the data storage and the computation will be managed by the database systems. So the time of data transformation can be saved, and some database techniques like index join can be utilized for efficiency. So to this end, this work uses a sparse representation to represent the matrix. And then this method works well for the sparse matrix, but it's not good for dense matrix because it incurs much storage overhead, and it cannot be highly optimized linear algebra libraries like BRAS. And to address this, so the UD user-defined function is proposed to compute the dot product of 2 vectors. It works fine for dense matrices. So for example, if we want to fit a simple model, we can just do it in database, but it just work well for the simple model, and some linear algebra optimization cannot be used because it is executed in the database. So the process saves the data transfer cost, and some database optimization can be utilized, but and costs are they just support simple machine learning algorithm and cannot support hardware like GPU and FPGA, and it negates the optimization of linear algebra in the machine learning algorithm. So let's see how to optimize the linear algebra expression. First is a rule-based optimization. It reduces the unnecessary intermediate results. For example, it transfers the X transpose Y to Y transpose X and transpose. So it passes the LA expressions to a DAG graph, DAG of operators, and rewrite with some rules. And if some matrix size is too large, we can use the distributed computation, and we can dynamic recompute for input matrix at runtime. but it is a rule-based method, so it needs heavy development efforts. So if the machine learning expression change a little, so the pattern can be recognized by the rules. So the spoof is proposed. The key idea is to transfer LA to the relational algebra, and then use the typical relational algebra optimization rewriting techniques to rewrite the relational algebra and then transfer it back to the linear algebra. So the many relational algebra optimization like join and aggregate can be utilized. And then that work, the spoof can now search through the whole space of the equivalent LA expressions. So the spoof is proposed to provide 7 rules for RA optimization. They prove that the rules are complete, and they use the equality situation to explore the rule space of the RA optimization. So the prompts are that the acceleration in a very fine-grained way, considering the machine learning expressions. And the other advantage is that the other acceleration technique can also be utilized. And the disadvantage is that it do not consider the optimization potential of the machine learning task where multiple tables are involved. So let's talk about the factorized machine learning. It considers the multi-tables, how to join them, how to run the machine learning algorithm without joining the tables. So in machine learning community, people always assume that input data are stored in a single table. However, the enterprise data are always scattered in multiple relational tables due to normalization. So data analysis must materialize data in a single table by drawing all the tables and export the data out of databases. This causes large computational cost and storage overhead, as well as data leakage risk. So factorized ML is proposed to address these issues by supporting machine learning on multiple relation tables and pushing the machine learning operators down to each single table. For example, we see that if we want to join the table S and R and to run a simple machine learning algorithm like the W transpose and multiply the X, and we can see that if we push down the W multiply S to each single table, we can save many computation operation. And also factorized method can reduce the redundancy of computation compared to the traditional computer after join weights. They are difficult to be applied as they need a complete implementation of machine learning algorithm, which takes too much effort. To address this, so the researchers develop a framework that aims to support a number of machine learning algorithms with few modifications efficiently. To this end, it defines a new data type called normalized matrix, connects the high-level machine learning algorithms and the low-level matrix computation operators. Then most all machine learning algorithm built on basic matrix operations can be implemented by the normalized matrix. So with this matrix K, the normalization information from origin data can be preserved, and the basic matrix operations such as matrix multiplication and cross product and matrix inversion can be implemented with pushdown. And furthermore, the learning task always needs a batch of join queries followed by aggregation. So the similar idea is always applied to push aggregations operator down to tables reduce the size of intermediate results, saving the joint cost. So queries in a batch can share the computation. So then let's talk about a more high-level optimization is computation graph optimization. In this part, many typical deep neural network architectures have become larger and deeper, resulting in a large number of computation resources. To solve this, it's natural to optimize computations in a CNN, which is defined as a computation graph of mathematical operators. So existing deep learning framework like TensorFlow and PyTorch optimize an input graph by performing greedy rule-based substitution on it. Each substitution replaces a subgraph matching a specific pattern with a new subgraph that is equivalent to the original one. For example, operator fusion integrates multiple operations into a single one, which removes the intermediate results. So the main challenge of the computation graph is that the search space of all equivalent computation graph is exponentially large, which brings huge costs and requires higher search efficiency. So existing deep learning systems solve this problem using a rule-based method that continuously improve the efficiency, but they may get stuck in the local optima. To solve the problem, so the method flow is proposed to establish a cost model to efficiently estimate the time usage of computing network, considering the rules with respect to the statistics like flops, memory usage, and number of kernel launches, and so on and so forth. Unlike PyTorch, MetaFlow considers the rules with increasing cost in the intermediate computation graph to seek more optimization opportunities. For example, as shown in the figure, a large substitution is first applied to a large convolutional layer, which in fact increases the intermediate total cost. However, after the subsequent substitutions that fuse operations like add and reload together, the final optimized computation graph can achieve a higher speed up. So the backtracking search over the relaxed substitution rules is applied to accelerate the computation graph processing. So to thoroughly optimize this problem, so researchers formally define it as a cost minimization problem, specifically taking as input an initial computation graph G, a set of substitution rules, the substitution length limit K, and a cost function. The optimizing computation graph problem is to find a graph substitution sequence P with less no more than K, such that the cost is minimized. The problem is proven to be NP-hard, and an efficient heuristic method with a polynomial time complexity is proposed for more practical usage. So hardwares are always utilized to accelerate the machine learning algorithm like GPU. Recently, many researchers have studied how to use specialized hardware design to accelerate the in-database execution of complicated data analytics. So the DANA is a work about the integration of FPGA and DBMS. So the challenge is manually leverage FPGA is tedious, and we need to write the FPGA code. So, and also the direct combining the FPGA and DBMS leads to inefficiency because of the limitation of the bandwidth of the GPU. So to address these, the key ideas are first, to automatically translate the UDF for execution on FPGA. We can use a Python package to encapsulate FPGA code. And to address the second challenge, they bypass GPU and its memory directly communicating with the RDMS buffer pool to saturate the FPGA bandwidth. And the second method is to integrate the column store DBMS with machine learning over FPGA to get high data analytic efficiency. So the challenges are, so in the column store DBMS, the SCD algorithm is always adopted, but it is poor in cache located, thereby inefficient. And the second challenge is that for the column store, we also need to compress and encrypt the data, so the efficiency is low. So the key idea is to leverage the FPGA to accelerate the SCD and the data compression using this parallelism ability. And the third one is about the GPU. So the motivation is that the transfer between CPU and GPU needs to go through the small bandwidth PCLU. So the solution is to purely use GPU for analysis without considering CPU. But this arises two challenges. One is the synchronization because between a large number of threads of GPU is very inefficient. And the second one is each thread is very weak in terms of the memory and the computation ability. So the key idea is to treat the thread block as a basic execution unit. And each thread block can process a tail of items, and it can improve the memory and computation ability. So the takeaway is that the training and inference steps can be accelerated using many DB-based techniques like linear algebra, factorized ML, and computation graph optimization. They accelerate mainly by optimizing the gradient computation across one or multiple tables, and the acceleration does not influence the model accuracy.
Now let's come to the final part, the post-ML, is the model management. So after deploy the model, we may have a large number of models to be managed. We should store them and query them. And then we come to the model deployment. And then the model should serve to the users. And at this time, we can debug the models, the machine learning pipeline based on the user's complaints. So first, let's see the model storage and query. So what data should be stored? So that it's model relevant data like parameters, gradient, information logs, and the training test data. So the key point is it's a model storage framework should be compatible to multiple machine learning frameworks, and the users can easily track the model, and there will be a user-friendly interface. And let's see, the ModelDB, it provides native client libraries that support different machine learning environments, and it has backend to store model and front-end to interact with users. And then the model hub manages deep learning large-scale artifacts. It can try different architectures and features and store many hyperparameters for fine-tuning. And it also provides gate-based model versioning and cyclic query for deriving new models. And it can publish, discover, and use models. So it can the model hub can list models, describe models, and compare models and evaluate the model. And it can also select the models and construct new models by mutating existing models and try new samples. And then we come to the model diagonals. So while the model development, there may be some failures. So we should know why does the model fail? Because of data or because of the model? So there may be some questions like which input pixels are the most important, how does the neurons work? So from the view of database, so there be a large number of parameters, vectors. So the model diagnose needs to check many parameters, which results in large storage cost and high computational cost. So our goal is to reduce the storage cost, to speed up the diagnose query and easy to use interface. So Mistake can efficiently store and query model intermediates for model diagnose. It supports both traditional ML and DL model. So it can query the learned parameters, log file, gradients, and so on and so forth. So to reduce the storage cost, it uses the quantization technique and remove the duplicates parameters. And it also provides a materialization technique that considering the trade-off between rerun the entire pipeline or save the model intermediates between the different iterations of the machine learning pipeline. Is a trade-off between storage cost and the query time. And there is also a cycling method for deep learning model diagnosis. It is to accelerate the execution of model diagnosis query by producing approximate yet acceptable results. It focuses on the representation in the latent space because vectors there can reduce the dimensionality of the data and it will be more efficient. And it also focuses on the decision boundary in the latent space because there may be many important vectors to check the outliers. And then after the model deployment, we come to the deployment and serving. So the model deployment is to deploy the model to production in order to serve for prediction. And the model serving is to support low latency and high throughput model prediction. And the goal is to guarantee low latency and high throughput and easy to use API. And the Clipper provides a low latency online prediction serving system. It decouples the application and models. And there is a model selection layers to improve the accuracy and a model abstraction layer to provide a user-friendly interface and bounding the latency and the throughput. And then we come to the machine learning pipeline that debugging. It is the debugging after the development stage, unlike the model diagnosis. It can also detect the data errors and model bugs. So RAIN is a typical system for machine learning pipeline debugging.
Hello everyone, I'm Xianhe Zhou. I found two very interesting questions in the chat window. I think the first question he asked for the AI4DB, if you had some comments about the emerging commonalities in representations being used for queries, workloads, metrics, etc. Would it be fair to say that some kinds of representations are understudied? I think yes, of course. Representations also called feature encodings are very important, especially for the learning-based methods. And I mainly have two insights. First, I think many representations are still understudied. For example, like the graph models, we still do not have very efficient methods to process them. Of course, you can represent the features as a graph model. However, whether the traditional methods that use like random walk or current very advanced methods that use graph embedding, like the graph convolutional networks, they all just extract information that they think are good for the downstream tasks, and then use the extract information sequentially, and then embed this information together as a high-dimensional vector, and then output to the downstream tasks. Still, there are information loss, of course. So how to efficiently prevent information loss and ensure the processing efficiency is a very key problem. Second, we have found that even today, the graph convolution networks or other graph embedding models, they all have to retrain the model if the graph changes. So they usually just use a very large graph to train a very large network, and then use the embedded representation to featurize the graph model. So okay, let me check. So it is a problem that how to efficiently process the model, process the features to represent them, and do not need to retrain for the representation process every time the input features changes. So I think these two important problems. One is trade-off, another is to avoid retraining and ensure the performance. For another question, let me check it. Do you see a relationship between the exercises of a well-defined standard benchmark? Yes, that's a good question. I do not see very well-defined benchmark, especially for AI4DB works. The key problem is that most AI4DB works, they require numerous training samples, especially for those supervised tasks. So the general method, but existing benchmark, they are too small. They just have few queries like GOB or TPCH. Well, for other benchmarks like Sysbench or TPCC, they do have many queries that you can randomly generate, but they are too simple. They are nearly the same and do not have very high values for the model to train, even if they have thousands or 10,000 queries that you can input into the model, but actually no many knowledge can be extracted. There are very sparse information distributed. And the maturity of development on a given task is, I think current applied AI techniques, they all have their shortage, because we only use some AI techniques for special scenarios, right? Because if the AI techniques, the most problem is that they cannot easily migrate from one scenario to another scenario, and they have the boundary problem. They only need to be solved if you need to migrate them, for example, from a Postgres circle to my circle. They are very challenging. You need to change the features, you change the knowledge that the model have learned. And if so, in which IDB tasks is more evident that need to for standards in testing to compare across works. I think there are some works that have tried for this target. For example, the most representative example is kinetic estimation. There have been many experimental papers that propose their benchmarks to compare with different kinetic works. they do have some, I think, very natural benchmarks that can be used. Two papers I think I've seen that will give the standard experimental comparison. And I think for the work itself, of course, the more crucial the work text is, the more important that standard benchmark is required, like the knob tuning, kinetic estimation, and query write. They all need very standard testing. I think is an important problem in the future. Yes, nice bench. Yes, I think that's a very good point. We also feel frustrated when there are no very powerful benchmark that can be used. And we usually just generate by ourselves, like use some useful tools like Circle Smith or others. The one you have mentioned, maybe I need to study offline, which I have not fully studied. Thank you for your comments. Thank you. Okay, thank you everyone. I think today's tutor has run out of time. Thank you. Bye bye.